Alright, so in this video I'm gonna be explaining another article about domain adaptation. As I said, unsupervised domain adaptation is the challenge, because supervised domain adaptation, we don't even care, it is already solved. And we are using a contrastive approach for that. And it is from Carnegie Mellon. This paper in 2019. So unsupervised domain adaptation makes predictions for a target domain data, while manual annotations are only available in the source domain. Previous methods minimize domain discrepancy, neglecting the class information, which may lead to misalignment and poor generalization performance. So of course, this one was the motivation of the previous video that you saw, that it was the same motivation. So to address this issue, this paper proposes contrastive adaptation network, optimizing a new metric which explicitly models the intra-class domain discrepancy and the interclass domain discrepancy. We designed an alternating update strategy for training this contrastive adaptation network in an end-to-end manner. Experiments on two real-world benchmarks of it, and of course most of the data sets are about computer vision, so NLP is still in its infancy for domain adaptation because it's hard. And comparison between previous domain discrepancy minimization methods and ours. The left one is the domain shift exists between source and target before adaptation. The middle one, class agnostic adaptation, aligns on source target at the domain level, neglecting the class label of the sample. So here we don't care about the class, we just want to reduce this gap. But the proposed method not only reduces this gap, which becomes this one, but also, as you see, the classes that belongs to particular things are separated. So triangles are separated and plus are separated. So it's at class level, and it is at the same time you're reducing this gap. So you see this target and the source are merged. Source and target are merged, are near each other. That's good. But also the class discrepancy is also can also be seen here. And so unsupervised domain generalization aims at improving the model's generalization performance in target domain by mitigating the domain shift in data distribution of source and target. So we have source domain samples, we have target domain samples, and we have these labels because we have M classes, and the target data is unknown. We know that they are from M classes, but they're unknown. So in the maximum mean discrepancy, our IID sample from original distribution of source and target. Formally, MMD defines the difference between the two distributions, P for source, Q for target. We reduce it. So this is the supremum of the expectation of f of x of source and f of x of target. But the proposed contrastive domain discrepancy is established on the difference between conditional data distribution across domains. Without any constraint on the type of the data distribution, MMD is convenient to measure such difference between P and Q. For example, for two classes C1 and C2, the kernel mean embedding for squared, this one is just E1, E2 is defined here. So this equation defines two kinds of class-aware domain discrepancy. So the CDD is calculated like this. We have intra-class and inter-class. We can separate it easily. So the overall objective, we need to minimize over multiple fully connected layers. Besides, moreover, we train the network with labeled source data through minimizing the cross-entropy loss. Therefore, the overall objective can be written like this. Beta is just the weight of discrepancy penalty term. And you see the training process. We perform alternative optimization between obtaining the target label hypothesis through clustering and adapting feature representation through backpropagation. For the clustering, we apply k-means clustering. Of course, instead of k-means, they could use, for example, Gaussian mixture models. But they use k-means. The number of clusters equal to that of the underlying classes, and the initial center of each class cluster is set to center of source data within the same class. The ambiguous data and ambiguous classes are discarded. For feature adaptation, the labeled target samples provided by the clustering stage together with the labeled source sample pass through the network to achieve their multi-layer feature representation. And they use this alternative optimization to deal with this situation. So iteratively, the clustering process is iteratively attaching labels for each target samples. We are attaching labels for each target samples, and then we are updating the cluster centers. Here we are updating the cluster centers till convergence or reaching maximum clustering steps, because time is limited. After clustering, each target is assigned a label same as its affiliated clusters. Moreover, ambiguous data, which is far from its affiliated cluster center, is discarded. We select a subset, which the distance is less than a threshold, and that threshold is between 0 and 1. Moreover, to give more accurate estimation of distribution statistics, we assume that the minimum number of samples assigned to each class should be guaranteed. The class which doesn't satisfy such condition will not be considered in current loop. So this is the algorithm for optimization of can at loop T sub E. We have source data, we have target data, but target data, you see, doesn't have a label because these Y's are labeled for source only. So we forward S and compute M cluster centers. So imagine we have, for example, 4 cluster centers. And then we cluster target samples using k-means, filter ambiguous target samples in classes. We don't want the outliers, so we filter those. So we go through a loop. First, we do class-aware sampling. Then we compute D, sample from source and compute this loss, and backpropagate the objective, then update the network parameters. So you have different domains: real domain, synthetic domain. For example, if you have a GAN, you say if it is coming from, if you're generating synthetically or it is real, you are fooling the discriminator by creating a better generator at each step. So we can go from any source domain to any target domain and see the effect of that. For any source domain, you go to any target domain. For example, for this paper, they have this accuracy. This is classification accuracy. Of course, Office 31 is very simple, so it's 99. And they use ResNet. But for some of them, is a little bit low. For example, if you go from this source domain to this target, it is 77. It is less than 85, which is low. Or different data sets you can see.